So this is what we have been discussing, crystal structure. And with regard to that, we have defined something called a unit cell, which can be repeated in space to generate the entire crystal structure. Okay. Now, if I come back to this once again, for our convenience, we can define a crystal coordinate system because we need to understand the geometry of the crystal in terms of planes and points inside the crystal and so on. So how do you provide the coordinates of a point, for example, in a crystal? If you want to do that, then you have to first define the coordinate system, right? So with this unit cell, we can again do that. So as I said, a unit cell is nothing but a convenient way of connecting the lattice points. So generally, the neighboring lattice points are connected in this way. All right. So this will give us a unit cell. So if you want to define the crystal coordinate system, you can again conveniently choose the origin, which is generally taken at the corner, at one of the corners of the unit cell. Okay. So if I have a unit cell like this, I could choose this point as my origin, and then here this is in 2D. So in two directions, I can define two vectors, one in this direction, let's say this is x, and another in this direction. So that is basically the edge length of the unit cell. So these are also known as basis vectors. So the unit cell can be described by these two basis vectors, A and B. A in one direction and B in another direction. If you consider this in the 3D, then there will be one more direction, X, Y, and Z or Z. So corresponding to that, you can have one more vector, C, which will be in that particular direction, in the Z direction. So A, B, and C would be the basis vectors when we consider 3D. Okay. In the 3D space, you will have these three vectors A, B, and C as part of this crystal coordinate system. Okay. And then you would also have the interaxial angles between these vectors. So we need to consider that also. So put together these two, that is the edge length of the basis vectors and the angles between them, will define the shape of the unit cell. Okay. If I consider this in 3D, then this will come across like this, right? So in the 3D, this is how the arrangement of the lattice points would be, how the lattice would be in the 3D space. So like what we have done in case of the 2D space, here also we can sketch out a small cell like this, right? The shaded one that you see over here. That's our unit cell in the 3D space. And now we can define this X, Y, and Z axis. In this manner. Okay. So here the basis vectors would be the edge length of the unit cell. Along x direction it is A, along y it is B, and along z it is C. Okay. These are also known as lattice vectors. And you also need to specify the interaxial angles alpha, beta, and gamma. Okay. Following the general convention, alpha is the angle between B and C, beta is the angle between A and C, and gamma is the angle between A and B. This is the general convention which is followed. Okay. You can see the same thing on the diagram also. Alpha, beta, and gamma are marked. So these parameters, that is A, B, and C, the edge lengths or the basis vectors, and alpha, beta, and gamma are known as lattice parameters, which will define a particular type of unit cell corresponding to a particular type of crystal structure. Okay. So we have defined the lattice parameters. All right. So you can have different types of geometries depending on the values of A, B, and C, and alpha, beta, and gamma. For example, if it is oriented in a manner, I mean the lattice points are arranged in a manner so that A is equal to B equals to C, and alpha is equal to beta is equal to gamma equals to 90°, then we have a cubic structure, a cubic cell that we can define, right? But not necessarily all the time this will hold true. You could have other relations also between A, B, and C. A may not be equal to B and B may not be equal to C. So depending on all such values of A, B, and C and the interaxial angles, you would have several types of unit cells giving rise to different types of space lattice also. And it has been found that there are 7 such combinations that can be worked out, and within that 7, all the structures can be accommodated. So this gives rise to 7 crystal systems. Depending on the values of these A, B, C, and alpha, beta, and gamma. Okay. One example we have seen, that is cubic, where A, B, C are equal and alpha, beta, gamma are also equal, and they are equal to 90°. Now, if we change this, if we see the other relations, we will find 7 such combinations, and that is the 7 crystal system. Okay. So this is listed over here in this table. As I said, for the cubic, we have this relation between A, B, C, and alpha, beta, and gamma. A, B, C are equal to each other, and alpha, beta, gamma are equal to 90°. Okay. Then we have 6 other, depending on how these are, these A, B, C, and alpha, beta, gamma are. For example, in the tetragonal structure, A is equal to B, but that is not equal to C, right? But this is again the same like the cubic system. Alpha, beta, gamma are all equal to 90°. Then we have the orthorhombic structure, wherein A is not equal to B and B is not equal to C, but alpha, beta, gamma are still all equal to 90 degree. Then we have hexagonal, where A is equal to B, but it's not equal to C. Alpha is equal to beta, and that is equal to 90 degree, whereas gamma is 120 degree for the hexagonal system, for the hexagonal structure. Then we have something called trigonal or rhombohedral, wherein A, B, C are equal, but alpha, beta, gamma are not equal to 90 degree, although they are equal to each other. Okay, alpha is equal to beta is equal to gamma, but they are not equal to 90 degree. So it's an oblique kind of cell that you have if you compare it with the cubic system. Okay. Then we have monoclinic, in which A is not equal to B is not equal to C. Alpha and gamma are equal to 90 degree, but beta is not equal to 90 degree. And finally, one more that I have missed here, that is triclinic, where A is not equal to B, not equal to C, and these angles are also not equal to each other. That's your triclinic system, triclinic structure. So these are the 7 crystal systems that you have, what you can see on this table. Okay.